Okay, so continuing on, we already talked about sort of the basics of astronomy and some of the history, and we're going to continue on with the history, but into the modern era where astronomy connects to physics and to science in a much deeper and more meaningful way. So that's our goal with chapter 3, is to understand what happens to astronomy sort of starting around the 1600s that really turns it into the science that it is today. Okay, so where can we begin? Well, the laws of planetary motion. So remember, when we look out at the sky, we see different things depending on the time of night and the time of year and where we're located. But if we map all of the constellations, they're always in the same positions relative to one another. We call these the fixed stars in the sky, and those form the celestial sphere. And then along roughly the ecliptic, which is the path the sun takes around the celestial sphere, we see a bunch of moving, wandering stars, which are actually the planets, and predicting where they're going to be in the future is a very challenging thing to do. Ptolemy was able to do it with reasonable success, but his method was really complicated. He had to use all of these epicycles because he was viewing the Earth as the center of the solar system, which turned out to not be correct. Copernicus was able to make a lot of progress in simplifying the planetary laws of motion, but he still needed epicycles even in his heliocentric model, where the sun was at the center, in order to explain very precisely where the planets would be in the future. And in addition to all of this, the laws of nature, so sort of a deeper understanding of what's happening and why, had not yet been uncovered in terms of the motion of the stars and the planets and what was happening out in outer space. To most people, the sort of heavenly realm was still seen as separate all the way up until the 1500s. It was imagined that it just worked in a different way under different rules than what was happening here on Earth. And what we'll see is that it turns out that's not quite true. Okay, so where do we go from Galileo? Well, actually, a little bit before Galileo, so backing up a little bit, we had Tycho Brahe and Johannes Kepler. And so Brahe was actually the last great pre-telescope astronomer in Europe, originally in Denmark. He took data for over 20 years on the exact location using astrolabe and a bunch of other tools, the exact locations of the planets and the stars over 2 decades. Very, very good data. And he invented a bunch of techniques to make this data much easier to work with, including using logarithms. And his student, who he actually hired as a mathematical assistant, was Kepler. And he didn't actually hire him until he moved to Prague, which is in modern Czechia. And he only worked with him for around a year, so not very long was their relationship. But in that time, Kepler was able to apply his mathematical expertise to Brahe's extensive data. And through this, Kepler was able to notice some really important patterns, which we now know as Kepler's 3 laws. So they're laws of nature about planetary orbits. Okay, so what are they? Well, his first law is relatively straightforward. It's that planets don't orbit in circles or with circles within circles, the epicycles, that their orbits are actually ellipses. So an ellipse is like an oval. It's this picture in the top right. And so Kepler's first law, the way we usually say it, is that a planetary orbit is an ellipse, so an oval, and the sun is at one of the focal points of the ellipse. And so actually in your homework, you'll get to see a little bit more about what those focus points are, those foci. They have to do with how you construct an ellipse if you want to draw one. So the sun is at one, the other is just empty. A circle is what happens if you make these 2 foci be at the same location. It stops being an oval and becomes a perfect circle. So a circle is a special case of an ellipse, but in general, planetary orbits are slightly not circular. Now, even more generally, planetary orbits don't just have to be circles or ellipses, they can also be parabolas or hyperbolas. And it turns out all of these shapes together are known as conic sections. Because if we take a cone, like an ice cream cone, and we chop it, then the shape of the sort of chopped off region, that, like if you used it as a stamp, that can either be a circle, an ellipse, a parabola, or hyperbola, as shown in this picture here. And so if something is in a bound orbit is one where it's kind of stuck, it's attached to the star, it comes back to the same place, then that has to either be a circle or an ellipse. But if something is in an orbit where it is not bound, where it's free, then that can form either a parabola or hyperbola. So for example, there's a random rock that we've observed called Oumuamua, which I believe is from Hawaiian language. And its orbit is actually hyperbolic. That's this picture here. And that's because this object, this rock, originated outside of the solar system. It happened to pass by pretty close to the sun, and then it's going to leave the solar system and never come back again. And so that still follows Kepler's first law, because that orbit is still one of these conic sections. Okay. What about Kepler's second law? Well, he also noticed from all this data that Brahe had saved for him that when planets are making these orbits around the sun, that basically they go faster when they are closer to the sun, and they go slower when they're farther away, and they do it in a very special way. So if we look at this picture here, we see that we can imagine the orbit as kind of like an ovular pizza. And if we slice this pizza, if we cut it once and then we let the planet move for, let's say, a week, and then we cut it again, we would get this blue slice of pizza here. And if we do the same procedure at a later time, so we cut the pizza, this orbital pizza, we let the planet move again for the same time, a week, and we cut it again. When it's on the far side, we get this much skinnier slice. But because it's longer, what happens is really special. The longer and the skinnier aspects balance, and so the slices on the left and the right actually have the same area. I want you to pause for a moment and think about how impressive it was that Kepler was able to realize this from a bunch of data, just seeing a planet in the sky. Like sometimes it's here, it's here, it's here. Maybe it looks like it's moving backwards, as we talked about in the previous lecture. It's here, it's here, it's here. Just from all of this data, where the planet is in the sky, he was able to put this picture in his mind of that planetary orbit around the sun on an ellipse, and was able to figure out that it moves faster whenever the planet is closer to the sun on that elliptical path, right? Because the sun is just at one foci, so it's off center a little bit. Okay, and finally, Kepler's third law is the one that's in some ways trickiest. It's the one where we need an equation. And what it says is that the period, so a period is basically the length of time that something takes to repeat. So the period for Earth rotating around the sun is 1 year. It takes 1 year for us to get back to our spot in orbit that we started at. So if we take the period squared, so 1 year squared, that it actually is equal to, in certain units, the roughly the radius, and it's an ellipse, so we have to be a little careful, but roughly the radius cubed. Now, it's not quite the radius. It's really what we call the semi-major axis length. So if I grab my pen really quick, so if we measure the length from the center of the orbit, which is not where the sun is, remember the sun is at a focus, but from the center to the edge, this is our length A. In math, we call this the semi-major axis length. And so Most of the orbits in the solar system are pretty close to circular, even though they're not exactly circular. So this distance is going to be pretty close to the radius of the orbit. Right, a circle just has one number, the radius from the center to the edge, whereas an ellipse has two. It also has this semi-minor axis length b, which is going to be smaller in the case of an ellipse. So anyways, Kepler's third law then says that if we take that distance cubed, that's the y-axis in this picture, and the period, the year length squared, that those two are equal to each other. So for the Earth, we can make this very nice. We say the Earth year is 1 year, 1 squared is 1, and the Earth semi-major axis length is 1 AU, 1 astronomical unit, which remember is 1.5 times 10 to the 8 kilometers. And so 1 AU cubed is also 1, and 1 equals 1. 1 squared equals 1 cubed, so that's the Earth in this picture. Now, we can look at some other examples. So for example, Mars has a period of 1.88 years, and it has a radius, roughly, right, a semi-major axis length of 3.5 AU. It's about 3 times farther from the sun than Earth is, roughly. And so if we cube the 3.53 and we square the 1.88, we actually get the same number, around 10. Either way, that is Kepler's third law. We can see that it works roughly for all of these planets, so that's why they're all in a straight line when we plot a cubed on the y-axis and p squared on the x-axis. Okay, so this is roughly what Kepler did, was he knew if he could get these in a straight line, he would have a relationship. And so he played around with it. He was like, do I square it? Do I cube it? What do I do? He didn't know why it worked. He just had a lot of data and was able to find this really clever pattern that we still use today. Okay. Okay, so like I said, we have this example with Mars. We can look at another example here. So what if we have a random planet with an orbit with a of 50 AU? So here, A is 50 AU. This is our A. So what do we do? Well, we can cube it. So what is 50 times 50 times 50? So A cubed would be 125,000. And then that's going to equal P squared. So, okay, now we need to square root both sides. So we can get P, and P is about 350 years. Okay. And so this planet, it's really far away, right? 50 times farther than Earth roughly is from the sun. But it also takes a really long time to orbit. It has to go farther. It's also moving slower. And so as a result, it has a very long year. Okay, so every planet has its own year, which we can confusingly measure in terms of Earth years. And that's what we're doing here. We're able to predict that using Kepler's third law. Okay, so we're going to fast forward a little bit from Kepler to Newton. So Newton was actually born the year Galileo died. So Copernicus was the early one in the Enlightenment, and then Brahe and Kepler were a little bit after him. So they were using his heliocentric model. And then Galileo was a little bit after that, and he was the one who invented the telescope. And then finally, we get to Newton. So what did Newton do? A lot of things. He did a lot of things for physics and astronomy and other sciences. But really what his genius was that he was really good at connecting equations to physical laws in a way where they were applicable everywhere. So he was able to see this idea that we still use today, that the laws of the universe, the laws of physics, are the same on Earth and out in space. And so we need to find some way to connect these two realms with the language of math, ideally. And so that's what Newton did. So the first thing was that he had his 3 laws of motion, which you probably have heard before in a science class. Basically, the first one is that the speed of something stays the same unless somebody pushes or pulls on it, a force acts. So if something's sitting still, it tends to stay sitting still. Confusingly, if something's moving, it tends to stay moving unless there's a force. Now, on Earth, there's almost always going to be friction because we have an atmosphere of air and we have things often are rubbing against each other. Out in outer space, there tends to not be friction, right? There tends to be nothing around and no air. And so once something starts moving in space, it tends to just keep moving. This is the brilliance of Newton. He realized that's also true on Earth. It's just usually there's something pushing or pulling on you. Now, the second of Newton's laws gives us a way to relate how hard we push or pull with how much something speeds up or slows down. So that's Newton's second law. If you're familiar with physics, you may know F equals ma. That's the way we write that as an equation. So the thing that relates the two is the mass of the object. And lastly, the third law, the most famous for rap lyrics and other poems and things, is that every action has an equal and opposite reaction. So if I push on something, I apply a force to it. It applies a force back onto me. It's the same size, it's just the opposite way. So if you imagine if you're ice skating and you push someone, they're going to move forward and you're going to move backwards. The same thing happens in outer space. Okay, so on the topic of Newton's laws, we should talk about a few vocab words. So one of them is momentum. So Galileo and Newton both worked with this idea of momentum, which is mass times velocity. So something like a semi-truck, if it's moving, it's going to have a lot of momentum because it has a big mass. A bullet fired from a gun will also have a lot of momentum because it has a big speed, a big velocity. So when we multiply these two together, that combination basically tells us how hard it is to stop something or to start it moving to that speed. So momentum it's related to how hard it is, how much oomph, how much punch something has. Okay. Now, if we separate it out a little bit, the mass part of the mass part of momentum, we have a special name for in physics. We call it inertia. So mass and inertia, they're really the same thing. But basically, the more mass something has, the harder it's going to be to move. Hopefully that feels pretty intuitive. And so in physics, we just say, okay, something has a lot of inertia if it has a lot of mass. And so the more inertia something has, the more difficult it is to move. That's basically Newton's second law, another way of saying it. We'll come back to these ideas when we talk about rockets and launching rockets. So the fact that rockets have to carry their own fuel means that they're really restricted due to momentum. It gets very, very hard to make a rocket go even a little bit faster. We're going to see why that is. But Newton, when you take all of Newton's laws together, they actually tell us something special about momentum, which is that it's a conserved quantity. So in this picture on the right here, we have two balls that are going to hit each other. So at first, one ball is moving left, the other ball is moving right. So their momentums are actually going to cancel if they're going the same speed and have the same mass. So the initial momentum here is actually 0. When they collide, they're going to knock against each other and they're going to shoot out the other way. But you see now they've just swapped. Now the one that was going left is going right and vice versa. But the total momentum is still 0, right? They're still canceling out. One's one way, one's the other. And so we're not going to do much physics in this class, but if you take a physics class, you'll learn a lot about how this works in detail and how to use equations to calculate this. And that's exactly the kind of thing that Newton and Galileo were doing when they were trying to understand the motion of the planets. Okay, so in addition to momentum, we also just, I know this is a random aside, but we should quickly talk about mass, volume, and density. Okay, so mass is basically just how much stuff is in something. It's similar to weight, but it's a little different, okay? So if you're on Earth, then the mass and weight of something are basically the same. But if we go to another planet, the amount of stuff in something does not change. So if I go to Mars, my mass has not changed, but on Mars, gravity is weaker, so I would weigh less. So you see how it's, when we're dealing with astronomy, we have to be careful. We're going to think about places that aren't on Earth, and so we need to be specific. When we say mass, we mean how much stuff is in something. That's our inertia. That's what goes into momentum. When we say weight, we mean how much force the gravity of a certain planet is pulling on a certain object. Okay. On Earth, these are very closely related, but elsewhere, it gets a little more complicated. Okay. Volume, hopefully, is pretty easy. That's just how big something is, right? So we can talk about gallons of water. That's a volume. We can also talk about cubic meters. So when you get an apartment with tall ceilings, maybe you have more volume in your apartment, so you could pack more stuff inside of it if you were wanting to really fill it up to the brim. So then density is how much stuff there is per volume. So we intuitively know that some materials are like heavier if we have a similarly sized chunk. So for example, if we have some gold, it's going to be heavier than if we have a similarly sized piece of rock. Gold will be like a very heavy rock. Or for example, iron is going to be much heavier than the average rock. That's why we build our weightlifting machines out of iron. And so density is the way that we quantify this idea, basically how packed in is the stuff inside a material. The more packed in it is, the more dense it will be. So we measure density in units of mass per volume. So here, grams per cubic centimeter, that's a pretty typical way to measure density. Okay, with that out of the way, we have one more quick definition, which is angular momentum. So regular momentum is like how much mass and speed something has when it's typically when it's going in a straight line. But if something is spinning, like planets, we know Earth spins, and we also know Earth rotates, which around the sun, which is kind of like a spin as well. So when something like a spin is happening, we don't want to use regular momentum. It gets a little too complicated with the math. So we define a new thing, angular momentum, which is useful when something is spinning or rotating or orbiting. And so just to give you some basic intuition, because angular momentum is mathematically a little tricky, but generally the more stuff there is in an object and the farther away it is from the center where it's rotating, the more angular momentum it'll have. And the faster it's spinning, the more angular momentum it'll have. And a nice thing about momentum and angular momentum is they're both conserved quantities. They tend to want to stay the same even when other things change. And so as an example, if you've ever gone ice skating or even rollerblading or just sat in a desk chair that can spin, you can try this out yourself at home, right? In your desk chair or on your ice rink. You can stick your arms out and start spinning, and you're going to spin as fast as you can. But then if you pull your arms in while you spin, then you'll start going even faster, which feels weird because you're moving your arms in. You're not like, spinning in a windmill or something. But this is conservation of angular momentum. What's happening is the angular momentum, when you pull your arms in, it doesn't change. So if you pull your arms in, you're bringing mass closer to your axis of rotation, which is part of what angular momentum is. So the only way for it to not change is for its other aspect to get bigger. You've made one part of it smaller, so the other part has to get bigger. That other part is this rotational speed. So if that's a little confusing, don't worry about it. This isn't a physics class. I encourage you to take one to learn some more. But we are going to come back to these ideas, and this is exactly the kind of thing that Isaac Newton was thinking about when he started to really study planetary motion. Okay, so what did Newton realize? Well, like I said, Newton's real genius was that he realized that the rules of physics on Earth are the same as the rules of physics out in outer space. And so it turns out that weight, right, gravity, the way that it acts on us here and the way that it acts on planets around the sun and on moons around planets, all these sorts of weird, celestial motions, that this is the same rule. We actually can write it in math, so we're not going to really do that much for this class. But again, if you take a physics class, you'll get to go in a lot more detail. So the force of gravity, F, is basically related to each of the two masses that are pulling on each other, mass 1 and mass 2. There's a constant, capital G, which is Newton's constant. We named it after him. And then we have to divide by the distance separating them squared. So if things are far apart, gravity is not going to be very strong between them unless they have a lot of mass, which things like stars and planets do have a lot of mass, so they can pull on each other even when they're pretty far apart. But if you imagine if we have a little golf ball and a planet that are far apart, they're not going to pull on each other very hard. And if we have two small objects, it won't matter how close we get them, we will still not get much gravity pulling on the two together. Okay. So this is Newton's brilliance. He realized that gravity was the same everywhere and that we could write it down mathematically so that we could actually calculate things with this. Okay, so then where do we go from here? Well, Newton took his new laws of motion, his new equation for gravity, and these ideas like angular momentum, and he used them to actually to prove Kepler's laws. So Newton showed basically that his laws of nature, his physics, was actually more fundamental than Kepler's laws, right? Kepler's laws were very useful and very interesting, but they're only true for planets. Newton wrote down a framework of physics that works on Earth and in space, and he was able to show that his framework could lead to Kepler's laws, that you can get, for example, you can start with his equation for gravity and show that planets have to move in an elliptical orbit if this law of gravity is true. And he did that for all three of Kepler's laws. I just wanted to show you a picture here for how to show the first law. It's okay if this doesn't make sense. This is something that you would cover in an advanced physics class, but I want to just show you a little bit of what it looks like. And you can feel free to look into this on the internet yourself or ask me about it if you want to learn some more details. But you can see why we think of Isaac Newton as one of the greatest physicists in our history. It's because he was able to make these really deep philosophical connections and then actually get results, which is very important as well. Okay, so carrying on from Newton, we should talk a little bit about planetary orbits. We already saw this with Kepler's laws, but basically if we have an elliptical orbit, then it'll have three main properties. So it has the period, which is how long it takes to go around. It has the distance, how far is the center of that orbit to the farthest away point. That's the semi-major axis A. And it also has something called the eccentricity, which is a little bit of a weird variable, but it basically tells you how circular your orbit is versus how ovular. So if your eccentricity is 0, then you're a perfect circle. And if your eccentricity is 1, then your ellipse kind of collapses and becomes like a hyperbola, or a parabola, I should say. And so what I want you to see here is that Mercury has a pretty big eccentricity, 0.2. So Mercury's orbit is not very circular. It's kind of more like an oval. But the rest of the planets have very small eccentricities, right? Earth has 0.02, so it's very close to a circle. But astronomy is a precision science. We want to know exactly where things are going to be in the night sky, because if we want to predict things into the far future, any errors we make are going to add up over and over again, and we're going to be really far off. And so we have to take into account all these little details. Even though it's pretty close to a circle, we need to make sure that we're being careful when we do real astronomy calculations. Okay, so just as an aside, we'll again talk about this in more detail later, but I want to briefly introduce the idea of satellites and other spacecraft. So when we have an orbit, in order to stay in orbit, something has to have enough speed. Okay, so I want you to think about this puzzle for a minute. The Earth and the Sun are pulling on each other. So why is it that the Earth doesn't just fall into the Sun? Why does the Sun not just suck the Earth towards it, and then we would all die, in a fiery explosion or something? And it turns out the answer is that the Earth has enough speed that it stays in orbit. Now, an orbit actually is still falling. So I want you to look at this picture here. There's a person standing at the North Pole, and they're going to throw like a baseball. They're really tall, and they're going to throw it really hard. So you see how if they throw it pretty hard, that's path A, it's going to go all the way from the North Pole, and it's going to hit down in Alaska or something. Okay. If they throw it harder, it's going to go all the way maybe to Hawaii. But if they throw it really hard, because Earth is curved, basically the object keeps falling, but it's moving so fast sideways that it keeps missing the Earth. Because the Earth is curved, it keeps curving around with the Earth, and that's the basis of an orbit. So when the Earth and the Sun are pulling on each other, they want to fall into each other, that's still happening. The Earth is trying to fall into the Sun all the time, but it's moving sideways fast enough that it keeps missing. It keeps missing the Sun, and it traces out a circle. So that's what an orbit is, really, or an ellipse, I should say. And so because we've been able to invent rockets, which can move things very fast, we're actually able to put little doodads, little satellites into orbit around Earth. And that's really useful, right? We can use those to communicate with each other over long distances, to take pictures of the Earth, to send satellite television, right, to someone's home, and a bunch of other things as well. A lot of experiments and scientific progress through these satellites. And so in California, we actually can frequently see these satellites being launched. So this is a picture someone took in SoCal of one of the SpaceX satellite launches that frequently happens nearby. And this is just a picture of one of the, I think this is a European Space Agency rocket that's used to launch satellites as well. So these satellites, they seem to go up, or the rockets, they seem to go up, but they actually always turn once they get pretty high, which you can kind of see in this picture, because they need to get enough sideways motion that they can just constantly miss the Earth. You have to do it high up enough that you're not in the atmosphere, right? You don't want to be constantly slowed down by hitting the air. So we need to get far enough away that we are outside of the atmosphere, and we need to go fast enough that we can constantly avoid the Earth. And the farther away you go, Kepler's third law tells us, the farther away your satellite is, the slower it needs to go. So it can go pretty slow once you're far away, but if you're far away, you have to have a lot of energy to get out of Earth's gravity, right? That takes a lot of energy too, so there's a trade-off. Okay, so on this note, we can actually define 3 cosmic velocities. These are specific to Earth and our solar system. So the first one is the slowest you can go to get into orbit. Okay, so if we want to get into orbit, what's the slowest we can go? It turns out that's around 8 or 7.9 kilometers per second. Pretty fast, okay, pretty darn fast. Remember, there are 3,600 seconds in an hour, so this is many thousands of kilometers per hour. Okay, to escape Earth, we have to go a little bit faster than that. We need to go 11.2 kilometers per second. And then to escape the solar system, if we start at Earth, we have to go even faster, about 16.7 kilometers per second. So you can see these are all pretty similar to each other, but it's significantly harder to go faster and faster with rockets because we have to carry our fuel with us. So you have to get all your fuel going faster and faster. It creates what's known as the tyranny of the rocket equation, which I encourage you to look into. Okay. So what if there are more than two objects? So far we've been talking about what to do if there are two objects. If there are three objects, which we call the three-body problem, there's a sci-fi book and movie series named after this, then we have to think about the gravity between each pair. So with three objects, there are three pairs. If we have four objects, there are not four pairs. There's 1, 2, 3, 4, 5, 6. Imagine a square with an X in the middle. There's 6 pairs. As we go to more and more objects, the number of pairs increases more than exponentially. Okay, it's crazy fast. And so this becomes very, very difficult. Now, in general, with our solar system, if we're not trying to be too precise, we can ignore this. But the planets actually do kind of tug on each other as they pass by. And so our solar system is not just, the Earth and the Sun pulling on each other. All the planets do it too. And so it's a complicated system. We call this an in-body. So in is just a stand-in for a number. So it could be a three-body if there are three objects, like the Earth, Moon, and Sun. That's a three-body system. But it could also be a four-body, a five-body, a 10-body, a 100-body. And so nearby, the Jet Propulsion Laboratory, JPL, actually has a program that they run on a supercomputer where they solve these really complicated equations very precisely for the solar system so that we can send spacecraft out and not accidentally send them to the wrong place, right? If we send something to Mars, we want it to actually get there. So we need some very high precision. In physics, and including in my work, we want to study things like galaxies where there are maybe 100 billion stars. And so we need to do some really crazy computer work in order to model all of these interactions, all this gravitational, all these pairs. And so that actually is something that takes huge supercomputers to do and is still an active area of research where physics and computer science really have to work together to make progress. Okay. So we're almost done with chapter 3, but I want to show you where people were able to take this. So, okay, let me back up a bit. All the way in ancient times, astronomers by eye were able to notice that there were a few of these wandering stars, these planets in the sky. They were able to see all the way from Mercury to Saturn. So Mercury, Venus, obviously we live on Earth, so we don't see that one in the sky. So Mercury, Venus, Mars, Jupiter, and Saturn, these are the 5 historical planets that have been seen since ancient times. Now, Uranus technically can be seen with the naked eye, but it's very, very faint. It's basically the faintest thing you could possibly see, and it moves very slowly. So for a long time, people didn't really notice it or thought it was a star. Once the telescope was invented, a man by the name of Herschel, this is his famous telescope, one of the biggest in the world at the time, was able to actually notice that Uranus was moving relative to the stars, and so it needed to be something like a planet. He was able to figure out that this was a new planet that had not been known until 1781, pretty recently, right? Considering the rest of the planets have been known for maybe 5,000 years. But something was really odd about this planet. So once there was this new planet, everybody was very interested. They wanted to track exactly how it was moving. And they noticed that it wasn't quite following Newton's laws. It seemed to be wiggling a little bit in the sky when it shouldn't have been. And so they could have said, okay, Newton's laws are wrong, or we need to adjust them. But because everyone had tested Newton's laws so thoroughly by that point, they were really confident that Newton's laws weren't the problem. So what could have been going on? Well, if you see Uranus wiggling a little bit, maybe there's another planet tugging on it, messing it up, messing up your calculations. And so that's actually how we discovered Neptune. So a whole bunch of scientists working in a collaboration and also against each other, racing to be the first, actually used math and physics to predict where this new eighth planet would have to be in the sky in order to properly adjust the orbit of Uranus so that it followed Newton's laws. And we can see in this picture here, we have the real orbit marked here, and we have the predicted orbit by Leverrier, and they're pretty close to each other. And by having astronomers use their best telescopes to look in the sky, they were actually able to find by 1846 and actually spot Neptune in the sky. And then once they found it, they could just track it and figure out its exact orbit from there. So this was really a marvel of science and a great validation of Newton's laws that they were able to predict the location of a totally new planet that had not been seen before and is a very, very faint, dim, hard to see object. But this is the power of physics and astronomy working together, as we can develop laws of nature and we can apply them to outer space to great effect, right? Finding planets that had not been yet discovered. Okay, so we're going to end it there for chapter 3. So that was the last bit of the history up to the modern era of astronomy. And we'll pick back up in chapter 4, talking about some common astronomical effects in a little bit more detail. I'll see you there.